Welcome back to our channel. Today, we're diving into the fascinating world of astrophysics to explore 10 theoretical ways the universe could meet its ultimate fate. While these scenarios might sound like science fiction, they're based on current scientific theories and hypotheses. So let's embark on this cosmic journey together. Before then, make sure to press that red bell icon and share the video more and help reaching first 100 subscribers. The Big Freeze, also known as the heat death scenario, is a concept in cosmology that explores one of the potential ways the universe might evolve in the distant future. This scenario is based on the current understanding of the expansion of the universe and the behavior of energy over time. The universe is currently expanding, with galaxies moving away from each other. This expansion is happening at an accelerating rate due to the mysterious force known as dark energy. As the universe expands, the space between galaxies also expands. This leads to a gradual cooling effect because the energy density of the universe decreases. As galaxies move farther apart, the wavelengths of light from distant galaxies get stretched, causing them to become redshifted and cooler. As the universe cools down, stars will gradually run out of fuel. Stars generate energy through nuclear fusion, and once their fuel is depleted, they'll become dimmer and eventually fade away. Over an unimaginably long time, all stars will exhaust their fuel, and new stars won't form as gas and dust become too dispersed. As a result, the universe will become increasingly dark and cold. Entropy is a measure of the disorder or randomness in a system. The Big Freeze scenario is associated with the idea that entropy will continuously increase. In a universe with low energy and minimal interactions between particles, entropy would approach a maximum value. As the universe reaches a state of maximum entropy, there will be no more gradients of energy available to do useful work. All energy gradients will have leveled out, resulting in a state of equilibrium where no energy approach a maxi-transfer or useful processes can occur. In this scenario, life as we know it would not be sustainable. Complex structures like galaxies, stars, and even molecules would become increasingly rare due to the lack of energy and interactions necessary for their formation. The Big Freeze scenario concludes with the universe essentially reaching a state of heat death. This doesn't mean the universe will be hot, rather, it signifies a state of maximum entropy and minimal energy, where no meaningful processes can take place. The universe would be cold, dark, and devoid of any significant activity. Certainly. In an alternate scenario known as the Big Crunch, the universe could eventually contract and collapse, in contrast to the current observed expansion. This concept is based on the idea that the force of gravity might eventually overcome the expansion driven by dark energy, leading to a reverse process. Here's an explanation of the Big Crunch scenario. Currently, the universe is expanding due to the initial momentum imparted during the Big Bang and the ongoing influence of dark energy, which is causing galaxies to move away from each other at an accelerating rate. In the Big Crunch scenario, the force of gravity plays a significant role. If the total mass and energy density of the universe are high enough, gravity could eventually counteract the expansion and initiate a contraction. As the universe contracts, galaxies would move closer to one another. The contraction would cause the space between galaxies to diminish, leading to a reversal of the cosmic expansion. As matter and energy become more concentrated, temperatures would rise due to the compression of particles. The universe would return to a state of high density and extreme heat, similar to the conditions in the early moments after the Big Bang. Just as the Big Bang theory posits a singularity as the starting point of the universe, the Big Crunch scenario suggests that a singularity could mark the end of the universe's contraction. A singularity is a point of infinite density and temperature where the known laws of physics break down. The Big Crunch scenario implies a cyclical model of the universe, where the universe goes through cycles of expansion, contraction, and subsequent Big Bangs. This model is sometimes referred to as the oscillating universe. In September 2021, there isn't enough observational evidence to support the occurrence of a Big Crunch. In fact, current observations suggest that dark energy is dominating the expansion, making the Big Freeze scenario more likely. Dark energy is a mysterious form of energy that is thought to be responsible for the accelerated expansion of the universe. While our understanding of dark energy is still limited, the idea that its hypothetical increase could have catastrophic consequences for the structure of the universe is based on the concept of its repulsive nature. Here's how dark energy's increase could potentially lead to tearing apart galaxies, stars, and even atoms. Dark energy is believed to possess negative, which means it exerts a repulsive force that counteracts the attractive force of gravity. This negative pressure is thought to be responsible for the accelerated expansion of the universe, causing galaxies to move away from each other at an increase in the universe's current state. The expansion driven by dark energy is not strong enough to overcome the gravitational attraction between galaxies, stars, and other cosmic structures. However, if the amount of dark energy were to increase,
its repulsive force could eventually become dominant. As dark energy's repulsive force increases, the distance between galaxies could increase even more rapidly. Eventually, this could lead to a point where the gravitational binding within galaxies. Similarly, the gravitational pull that holds clusters of galaxies together could be overcome by the increased repulsive force of dark energy. This would result in the dissolution of these massive structures. Within galaxies, stars are held together. Gravitational forces. If dark energy's repulsive force becomes stronger, it could weaken the gravitational bonds that hold stars in their orbits, potentially leading to stars drifting apart from each other. The repulsive force of dark energy could also disrupt the stability of stars and planetary systems. If the repulsion between particles due to dark energy outweighs the attractive forces, it could lead to the disintegration of stars and planets. Atoms are held together by electromagnetic forces between their positively charged nuclei and negatively charged electrons. An extreme increase in dark energy's repulsive force could interfere with these forces, making it difficult for atoms to maintain their structural integrity. In the most extreme hypothetical scenario, if dark energy were to continue increasing without bounds, it could even overcome the nuclear forces that hold atomic nuclei together, leading to the potential disintegrate. The concept of a false vacuum and its potential collapse into a lower energy state is a fascinating idea rooted in theoretical physics and cosmology. It's important to note that this is a complex and speculative topic that involves advanced concept. In quantum field theory, the vacuum state refers to the lowest energy state of a quantum field. It's often thought of as the empty or ground state of the universe. However, the vacuum state isn't truly empty. It's a state of minimum energy with fluctuations of quantum fields occurring at the smallest scales. The false vacuum is a hypothetical state of the universe that appears stable but isn't the true lowest energy state. It's like a temporary hill in the energy landscape of the universe, and the true vacuum state is the stable valley. Think of the energy landscape as a series of hills and valleys, where each point represents a different energy level. The false vacuum represents a hill that the universe might be in, and the true vacuum is the lowest point in the valley. According to quantum mechanics, particles can tunnel through energy barriers even if they don't have enough energy to overcome the barrier classically. This is called quantum tunneling. The idea is that there's a small probability that the universe could tunnel from the false vacuum to the true vacuum, even though the false vacuum might seem stable over extremely long timescales. If this tunneling were to occur, it would lead to a lower energy state, resulting in a process known as vacuum decay. Once a small region of the universe enters the true vacuum state, a chain reaction could start. This would involve the rapid expansion of the true vacuum region at nearly the speed of light. Vacuum decay could have profound effects. Particles, atoms, and even entire structures could be torn apart as the new vacuum state's properties differ from those of the false vacuum. This would propagate as a bubble of. The scenario where the universe ends in a sea of fading black holes is based on the idea that black holes, which are incredibly dense objects formed from the collapse of massive stars, will eventually lose energy and evaporate over extremely long timescales due to a quantum phenomenon known as Hawking radiation. Massive stars that exhaust their nuclear fuel can undergo gravitational collapse, leading to the formation of black holes. Black holes have such strong gravity that not even light can escape from them, making them appear black. According to Stephen Hawking's theoretical work, black holes are not completely black. Due to quantum effects near the event horizon, the boundary around a black hole beyond which nothing can escape, pairs energy. As they lose energy, their mass decreases, and consequently, their gravitational pull weakens. As black holes continue to emit Hawking radiation, their mass decreases further. Eventually, when a black hole's mass becomes sufficiently small, the rate of radiation emission increases dramatically. This marks the final phase of the black hole's evaporation, and it releases a burst of energy before disappearing completely. In the scenario where the universe ends in a sea of fading black holes, over a staggeringly long period, black holes of all sizes will gradually evaporate. This process will continue until the last black hole in the universe evaporates completely, releasing its remaining energy in the form of particles and radiation. As black holes evaporate, the universe will become increasingly dark and cold. Without the light and heat generated by stars and black holes, the universe's temperature will approach absolute zero. The universe will eventually reach a state known as the dark era, where most sources of light and energy have disappeared. The universe's entropy will continue to increase, leading to a state of maximum disorder and minimum energy. The universe will become dominated by entropy, with matter becoming more and more dispersed and interactions becoming exceedingly rare. It's important to note that this scenario is based on current theoretical understanding and hypothetical processes. As of now, We have no experimental evidence to confirm the long-term behavior of black holes or the occurrence of the described events. We've embarked on an extraordinary voyage through the realm of theoretical physics and cosmology, exploring captivating scenarios that stretch the boundaries of our imagination. These theoretical scenarios remind us of the intricate complexity that underlies the universe's fabric. From the grandeur of cosmic expansion to the subtle dance of particles, we've glimpsed the profound forces that shape reality. Let's leave with a sense of wonder, a reminder that the universe is a canvas of endless possibilities. Whether it's the allure of a distant star or the elegance of a mathematical equation, the journey of understanding is a lifelong adventure. Thank you for joining us on this journey of exploration and inquiry. If you've found inspiration in these scenarios, consider delving deeper into the realms of science and cosmology. The quest for knowledge knows no bounds. If you've enjoyed our cosmic voyage, don't forget to like, subscribe, and share to stay connected with our future explorations. Your support fuels our passion for bringing the wonders of the universe to light. As we sign off, remember that the universe's story continues to unfold, inviting us to dream, question, and marvel at the universe's breathtaking complexity. Until next time, keep looking up, keep wondering, and keep exploring.